Hello students, this is our lecture number 18 and today we are going to talk about a dining philosopher problem. This is our last classical problem that we are going to discuss under the chapter process synchronization, and this is our last topic in this chapter as well. So, um, before I am going about to the details about the dining philosopher problem, just to recap what we have discussed about the last class, right? So in our last class we have discussed about the uh, reader writer problem, wherein you have got only two different class of process and one shared resource. I repeat, there are only two different class of process. One is reader and the class is writer, and only one shared resource. So this dining philosopher problem is basically different one, the previous one. So it's a large class concurrency control problem, wherein you have got more than one resource and more than one classes. So you have got, I repeat, this is large class example of large class concurrency control problem, wherein you have got multiple resources and multiple process, right? So these resources has to be efficiently allocated to the requesting process. So that is the problem, and it is understood with the help of this dining philosopher problem. So we'll go about the problem in very simple form. Okay. Suppose there is a resource, right? Suppose there is a resource. Okay. This is the location of the resource, and I represent. Now I am going to use different representation for resource. So first is this. This is a bowl. Okay. This is a bowl which contains a rice. Okay, and these are the chopsticks. Okay. One, two, three. Okay. And there are philosophers which are known to be a process. Okay, I'll just encircle it with different color. Okay, so these are the philosophers. One, two, three, four, five. Please be careful how I have arranged it. Okay, so I have arranged this philosopher somewhere in between these two chopsticks. This is two chopstick, this is two. Between these two, any two chopstick, I have arranged this philosopher because the chair is available at that location. So there is reason. Okay, so I just repeat it. There is a resource, two different kind of resource. This green color and red color is the resource. This red color is a bowl which contains a rice. Okay, and to eat this rice, you need a chopstick. So this green color representation is a chopstick, and there are only this 5 number of chopsticks. 1, 2, 3, 4 and 5, and they are placed in such a way that between two chopstick a chair is arranged for the professor or the philosopher to sit. Okay, so this process, this circle one is known as a process or philosopher. Okay, so these are the philosopher. I'll just like to name it. So this is my philosopher 1, this is my philosopher 2, this is my philosopher 3, this is my philosopher 4, and this is my philosopher 5. Okay, so these are the process. Blue color are the process or philosopher, and this green and red color is the resource. So this is the rice and this green color is the chopstick. So now let us talk about the definition of the problem, right? So this philosopher or the process, this philosopher, so I don't like to take the name of the process, so let us have a common name only for explanation, that is philosopher. So I'll use the philosopher word. Okay. So this philosopher, the job of this philosopher is to think. The job of the philosopher is to think and eat. Eat. So the job of in the entire life of this philosopher, the philosopher will do only two different kind of tasks. Either the philosopher will think or eat. These two different tasks cannot be done at the same time. Once, if the philosopher is thinking, then it will not be able to read it, or if the philosopher is eating, then the philosopher will not think. And while thinking, they will not talk with each other. Okay, and their orientation is this, somewhere in the order, in this way, right? Wherein the philosopher will sit somewhere in the middle of the chopstick. Okay. Now, whenever the philosopher think, okay, whenever the philosopher think, it will not interact with the nearest neighbor, P1, P2 and P5. It will not talk. It will not interact it will simply think. Now, whenever philosopher will feel hungry, okay, suppose P1 is feeling hungry, or any of the process or the philosopher is feeling hungry, then it will hold the nearby chopstick. So if P1 is feeling hungry, P1 will hold this chopstick and this chopstick which is nearby to this philosopher. It's not happening that P1, that is philosopher number 1, is grabbing this chopstick. It's not happening that. It will grab two chopsticks which is very very close to each other, right? So now you might be thinking, like, if one of the chopstick is not available, then what will happen? All those things will cover it up. Okay. So at that moment of time, philosopher will either think or it. If if the philosopher is thinking, it will not interact with each other. If philosopher is hungry, okay, it will pick two chopstick. Okay, it will pick two chopstick which is nearby to each other. So whenever it picks up, it does not pick up at the same time. Okay, suppose at time t equals to t1, P1 has picked this chopstick. Okay, it is very very obvious that at time t equals to 2, it will pick this chopstick. It is not happening that at the same time, that is t1, it has picked two chopstick. So it's not happening that. Okay, so you need to take care of these two things. So P1 can grab the chopstick, only one chopstick at a particular time. Okay? And to eat, both chopstick has to be on his hand. Okay. Now once P1 has started eating, once P1 or the philosopher has started eating, it will not release the chopstick, and it will not release the chopstick involuntarily. Okay, it will release the chopstick in voluntary action. So once it completes its eating process, then it will release the both chopstick. So this, having said this scenario, let us go back to the problem. Okay, consider 5 philosophers who spend their life in thinking and eating. Right. So the job of the philosopher is to think and eat. And in this blue color are the philosopher, and these philosopher task is to eat and think. Now this philosopher is sitting on their chair, sharing the table which contains bowl of rice, which is located somewhere in the center, and there are chopsticks that are placed in this order or in this manner, right? So there are shared data is bowl of rice, okay, and chopstick. Let us forget about the semaphore. So shared data is bowl of rice and the chopstick. So we have a diagram here. We'll take help of this diagram now onwards. So the chairs are placed in such a way that the philosopher has to sit on the chair, and it will be sitting in such a way that in such an orientation that between two chopsticks the chair is placed. Okay. Now when philosopher is thinking, he doesn't interact with her colleagues or anybody. From time to time, again randomly, again continuously. You can consider it continuously. The philosopher time to time gets hungry. It's not happening that philosopher will eat at particular time and it will not get hungry. Okay, it may happen that it has ate just now and after some time he again feels hungry. Okay. So philosopher will get time to time hungry, okay, as and when he is doing the thinking task. Okay, so as and when he gets hungry, it will pick up the two chopstick which are very close to him. For example, for this, the two closest chopstick for him is this chopstick and this. So it's not happening that this chopstick will be picked by him. It's not happening that. The closest chopstick has to be picked by the um, philosopher, right? Kind of table manner, right? So tries to pick two chopsticks that are closest to him. Now the chopsticks that are between her left and right, so which I will recover it. Now whenever philosopher picks up this chopstick, it will pick only one chopstick at a time. So one chopstick at a time. So it cannot pick two chopsticks at the same time. Okay. And suppose suppose philosopher one is hungry, okay, and this chopstick is held by the P2 philosopher, because these two chopstick was like held by this P2 because P2 is currently eating at time t equals to t1. So at time t equals to t1, P2 is eating. Now at time t equals to t2, P2 now gets hungry. Now it will look for chopstick. So he will see that okay, this chopstick is free. Okay, he will pick this. Now again he will see that okay, this chopstick is not available. It is being used by philosopher 2. Now in that case, P1 will not snatch this chopstick from P1. P1 will voluntarily release this chopstick, then only P1 will be allowed to eat. So this is the scenario. Okay. Having said this, okay, philosopher, I'll just read it out. Philosopher may pick one chopstick at a time and cannot pick up chopstick that are already in hand of the neighbor. Okay? Now when the philosopher is hungry, both chopstick has to be in order to eat. So to perform the eating operations or to execute the eating operation, both chopsticks should be in the hand of the philosopher. Okay? And whenever the both chopsticks are available with him, he will perform the eating process. So during eating, he will not release the chopstick voluntarily. Okay, it involuntarily. It has to complete the eating process. Then it will voluntarily release its chopstick from wherever it has picked up. So whenever it finishes the eating, he puts down the both chopstick and start thinking again. Because after eating, it has to think again. So eating and thinking, then and then go one after another. So this is the problem. This is the problem of dining philosopher. Okay. So now one of the solution, okay, to this problem, because let me give you a scenario of a problem. Okay. So this is the definition of problem. So it may happen that suppose at time t equals to t1, okay, all the philosopher gets hungry and has picked their left chopstick. For example, so this chopstick was picked by this philosopher at time t equals to t1. This chopstick was picked by the P5 at time t equals to t1. This chopstick was picked by P4 at time t equals to t1. This chopstick was picked by P3 at time t equals to t1, and this chopstick was picked by P2 at time t equals to t1. Now see, after picking the respective chopstick by respective philosopher at time t equals to 1, now at time t equals to t2, it will wait for other chopstick to get released by another philosopher. So now In that case, what will happen is that since all of them have started eating at the same time, so P1 will wait for P1 will wait for P5 to release, and P2 will wait for P1 to release, P3 will wait for P2 to, like this it will go and cycle will be formed. So if this is the scenario, that it is never going to happen that any one of them is going to release the chopstick, right? So a deadlock situation may get encountered. So this is the problem and it should not happen. Okay, I'll just erase it. This should not happen. So this is the problem and it should not happen. So one of the simplest solution would be to signify each other that whether I am eating or not, whether the philosopher is eating or not. To signify that, you can take help of the semaphore. Okay, the semaphore chopstick, it's an array, it's a semaphore which is initially initialized to value 1. Okay, so I'll just show you. Suppose there is a array semaphore 5 1 2 3 4 5. So name of the semaphore is chopstick. So all inside this content the value will be initialized, and these are indexes 1 2 3 4 5. So if I talk about the array, I will start with the 0, but for convenience so I'll start with 1 2 3 4 5. This index means the identity of this philosopher. So if philosopher P1 wants to pick up the chopstick, it will make this 1 to 0. It will make this 1 to 0. So using wait and signal, it will try to pick up it. Okay. So now using wait and signal, it will try to pick up the code. Now this code is all about, I'll just explain briefly. When this first wait statement, wait chopstick of I gets executed, say for example the P3, that is P3 philosopher wants to eat because he has got hungry. So what will happen is that first this statement will get executed, wait chopstick of I, or so I is now 3. So if I is 3, so it will make this to 0. It will make this to 0 and it will execute next wait instruction. In the next wait instruction, what will happen is that in the next wait instruction, if you execute this, so chopstick inside bracket I is 3 plus 1 modulus 5. So next will be 3 plus 1 modulus 5. So answer will be 4. Answer will be 4. So chopstick number 4 will be picked. So next statement. So now if this is 0, then this P3 will be able to know that okay, philosopher number 4 is currently eating. So this is how you can use the concept of semaphore to solve the problem of concurrency that I have shown you just now. Okay, now suppose another example, let me give you another example. Suppose philosopher number 2 is hungry. Okay, I have started the indexing from 0. Philosopher number 2 is hungry, so chopstick of 2 will get 0. Okay, then again, now which chopstick need to be picked by this philosopher number 2? Chopstick number 3. So using this code, it will pick this next chopstick because 2 plus 1 is 3, 3 mod 5 is 3. So it will pick this chopstick by making it to 0. So whenever any philosopher is picking the chopstick, it will pick the current location. So I is 2, and next one will be next immediate one. Okay, so it may happen that it's not necessary that it has to pick this also. You may rearrange the formula in such a way that it can pick this also. So it's up to the user, okay, or it's up to the implementer. So this is one of the solution. So you can use the semaphore chopstick to pick up the chopstick and eat it. So these are the examples of the structure of philosopher I. With the help of which it can pick up the chopstick and perform the eating operation in an exclusive, mutual exclusive fashion. Okay, so this is all about the structure. Now, as I've told you already that due at particular point of time, suppose all the process have felt hungry at the same time and have picked the left chopstick at the same time by all. Okay, although it is very uncertain, but there is still a possibility, and this leads to a problem of deadlock situation, and it should not happen. Okay, so if this is a situation, then you need to find a solution to it. Okay, so basically I'm talking about if that is the solution, what should be the regulation that you need to impose while implementing it. Okay? So some of the suggestions or solution to avoid the deadlock situation is this: 1, 2, and 3. So first rule you may apply that you may apply any one of them. Okay, so you may allow only out of that 5 seat, out of this 5 numbers, you may only allow only 4 seat to be filled. So you may remove this chair, or you may not allow this chair to be used by the philosopher. Okay, so if at most one philosopher will be sitting, then what I'll just show you. Okay, I'll just show you. If this chair is not occupied by one of the philosophers, means basically one of the philosopher will not be sitting in this. Okay? Only 4 philosopher will be sitting around it. Chair. Now suppose this is picked by this chopstick is picked by P1, this chopstick is picked by P5, this chopstick is picked by P4, and this chopstick is picked by P2. So what will happen, although P1 and P3, P1 will wait for P5 to release and P5 will wait for P4 to release, but there may be some, after some time, okay, after some certain finite amount of time, P4 will be allowed to use it. P4, because this software is not held by any one of the process, because P3 is not there in the list. So P4 after some time will release this chopstick. It will release this chopstick. So when this chopstick is released, P5 can eat. P5 can eat. Okay. After completing the eating process of P5, this chopstick is released, which can be given to P1, and like that way the circular sequence can be broken, right? So circular sequence can be broken. So this is one idea, right? Now let's talk about another one. Suppose you allow the philosopher to pick up only both chopsticks if both are available. For example, you can have a look here and there. Okay. Suppose P3 was feeling hungry, so P3 will, okay, before picking up this, before P3 picks up this chopstick, it will check whether this can be picked up or not by checking the value. Okay, if it is 1, then it is very obvious that P4 is not eating it. That's why P3 can pick up. Once P3 pick up this, it can pick up this, okay, and eat it. Okay, so I hope I have made it clear. Allow a philosopher to pick up only both of the chopsticks are free. So if the both of the location are 1-1 or both of the chopsticks are free, then only pick up. Okay, else don't hold the resource. Okay, because you cannot complete the task by holding the resource. So if you cannot complete the task, don't hold the resource. Okay. And the last one is the asymmetric solution. It's very simple. Okay. It's very simple. I'll just give you a brief of it. So all the philosophers are numbered. Okay. So some of the philosophers are odd number and some of the philosophers are even number. Okay. I'll just mark it which are odd number and which are even number. So philosopher this 1, 5 and 3 are even numbered philosopher, and philosopher number pink, this 1, 2 and 4 are even number. So now what you can do is that you ask the philosopher even number philosopher to pick up the left chopstick first and then right chopstick. Okay, or you can ask the or implement the odd number philosopher to pick up the right chopstick first, okay, and then the left one. So if you follow this uh, rules, okay, any one of these rules, you will not be entering into the deadlock situation. Okay, so that's all for today. So if you have any questions, you may please post it up, or you may bring up in the our discussion session in our regular class or the remedial class. So I'll just give you a brief about it. The dining philosopher problem, the problem of last class concurrency problem, where there are 5 philosophers sharing the rice located at center and sharing the chopstick. Job is to eat and think. Okay, whenever whenever they think, they will not interact, and whenever they feel hungry, they will start eating it. But for it, they need to have a chopstick in both their hands. When they eat, nobody will disturb it. Okay, it will release after eating. It will release the chopstick voluntarily. Okay, so to perform the eating process, both chopstick has to be available, and detailed I've already talked with it. So one of the simplest solution to solve this kind of problem, where you may enter a deadlock situation, is with the help of the semaphore chopstick. So this is the how this is shared variable by all the semaphore variable by all the philosophers or philosopher variable. So the first weight will allow you to pick up one chopstick, and uh, next this weight instruction will be allowed used to pick up the next chopstick in sequence. Okay, like for example 2 3 1 2, like that way. So that's how it works. Okay, so now the in very worst situation, it may happen that you may enter in a deadlock situation. So to avoid that, you may impose some of the regulations as mentioned in the 1 2 3, which I've already covered up. Okay, thank you. Now after this, there will be a monitor. Okay, so the monitor section will be covered up by the student itself as a part of the self study. So you can refer the book and the slides that's already available in the web. So that's all for today. Thank you so much.